Okay, we are recording right now. So let me go ahead and share my screen to show you guys what's in Schoology. And of course, we're going to begin by getting deeper into the lesson that we started on last class period. Okay, so okay, we are currently in fifth period. Fourth 6 weeks, and today is March the 11th, and it is a Thursday. Okay, so on today, um, we're going to continue our discussion into harmonic motion, specifically talking about waves. So we're going to go over these waves notes, look at a few examples from this PDF file, and then as soon as we're done with that, you guys should have enough knowledge to do the waves assignment um, that is currently posted in Schoology and due by midnight tonight. Okay, it's a multiple choice assignment. And again, as long as you pay attention to what's going on today, you should be good on how to work out all the questions in that assignment. Okay, so let's start by reviewing what we talked about last time. Last time I introduced harmonic motion. And remember what I told you guys. Harmonic motion deals with modeling processes that repeat themselves. So that's what we're talking about in this particular topic of physics. We're modeling processes that repeat themselves, and we're modeling those processes mathematically and graphically. So, what is a process that repeats itself? Let me give you guys an example of this, as I mentioned this to you guys last time. So, um, so on my screen here, you guys clearly see a spring attached to a block. And you guys can imagine someone taking this block, pulling it back and releasing it, and the spring in the block just keeps swaying back and forth, back and forth, back and forth. Guys, this is an example of harmonic motion. Why is it? Because it's a process that keeps repeating itself. It repeats itself over and over and over again. So physicists need to find ways to figure out how to model this process mathematically and graphically, to understand it in its details. And the reason why we want to do this is because this sort of process happens in our everyday lives. So, for example, imagine the atoms that make up who you are. Those atoms, those molecules, they're oscillating, they're vibrating. So, oscillations and repetitive motion occurs all around us. So, this is why physicists need to be able to describe that motion in the real world. So, of course, we're not going to talk so much about the kinetic energy and the total energy of the system. That's something more for AP physics. Here, we just want to focus on modeling the simple things like period and frequency and things like that. Okay. So, what exactly is period and frequency? Remember what we talked about last time? Period just represents the amount of seconds it takes for an object to go one cycle. Okay, the amount of seconds for the object to go one cycle. In other words, how long, whereas frequency means how often. Okay, so period means how long is one cycle. Frequency means how many cycles are um, are are taking place in any given amount of time. Okay, so period means the number of seconds in one cycle, whereas frequency means the number of cycles in 1 second. So, and it's important that you guys know how to find that. And I want to remind you guys what we did last time. So, imagine this example of a Ferris wheel here. So, okay, okay, you guys clearly see that this Ferris wheel is moving in a circle, and this process just keeps repeating itself. It keeps repeating itself over and over again. So clearly, this is an example of harmonic motion because it's a process that is repetitive. Okay. Now, how can I figure out what is the period of the Ferris wheel? Well, this is easy. All I would need to do, I would just need to take out my stopwatch on my cell phone, And guys, look at the yellow box. When that yellow box come around to the top, I'm gonna start my watch. I'm gonna start my stopwatch. So when it comes to the very top, start. Okay. So when I see the yellow box comes back around to the top again, I'm gonna stop my stopwatch. So stop. Okay. So on my stopwatch, I got 13.3 seconds. So 13.3 seconds is my period. I'm gonna write that down. So the period of the Ferris wheel was 13.3 seconds, according to my stopwatch. Hold on, guys, I'm beating up my pen, my computer pen. So the period of the Ferris wheel was equal to 13.3 seconds. Does anybody know how to find the frequency from this period? Anyone tell me? Remember, guys, the way we find frequency is to do 1 divided by the period. So we'll do 1 divided by 13.3. And that, when I do that, that gives me 0.075 hertz. Okay. So that's something you guys need to remember, because there's going to be a few questions on this assignment where you guys will need to find period and frequency. Right. So remember what period is. Period is the number of seconds for one cycle. So in other words, how long it took for this Ferris wheel to go around one time. Okay. So hopefully that makes sense. And then frequency will be the reciprocal of period. Okay. All right. Now, with that said, let us go ahead and get into our notes for today that are currently in Schoology for today. Okay, so these wave notes and examples, let me open these up in Kami. Okay, since we are talking about harmonic motion, hold on, guys, let me clear everything on the screen here, just to be sure. Okay, since we're talking about harmonic motion, this leads to an excellent discussion on waves. Okay, waves are a perfect example of harmonic motion. So if you were to drop a rock in water, you would make waves. You know that the waves move away from where you drop the excuse me. You know the waves move away from where you drop the rock, but when the waves pass, the water moves up and down. So this bobbing up and down with the water is an example of harmonic motion, which is what we're going to talk more about today. Okay. Now, in nature, there are two main types of waves that you guys need to be familiar with. You guys need to understand what is a transverse wave and what is a longitudinal wave. Basically, transverse waves are when vibrations move perpendicular to the direction of the wave itself. For longitudinal waves are when vibrations move parallel to the wave motion itself. So what do I mean by this? That vibrations move parallel and perpendicular to the wave? Well, in order to best explain that, I'm just going to show you guys a video of the two. In this first video clip right here, we're going to look at a simple transverse wave. this person is going to produce a transverse wave in a slinky. I want to show you guys how this looks like. It's better to see it to kind of understand the difference between the two. So here's our slinky, and notice how this guy's producing transverse waves in the slinky. Okay, they're going to play that in slow motion so you guys can see that. Okay, so that's an example of transverse waves being created. Okay. Okay. Guys, notice how that's different from a longitudinal wave. So in this video clip, watch how he produces longitudinal waves in the slinky. So look at this here. Okay, you guys see the difference? Okay. So notice in this example here, he's pushing his hand forward and backwards, in the other example, he was shaking his sand side to side. So clearly he's producing a different type of wave. Okay, so here's the basic idea here. So guys, in this particular example right here, okay, notice how his hand is going side to side, side to side, side to side. But the pulse of energy is traveling, in this case, from this point on the slinky all the way to that point of the slinky. So in other words, the pulses of energy are traveling perpendicular to the direction the wave is moving. Okay, so guys, see how like his hand is going side to side, side to side. In this case, I'm gonna say his hand is moving in the y direction, whereas the wave itself is traveling in the x direction. Now the pulses of energy are traveling in the x direction, so it's clearly perpendicular to the direction of wave propagation. But notice how this is different here. So in this example right here, notice how he moves his hand forward and backwards, forward and backwards, forward and backwards, forward and backwards. So in this case right here, his hand is vibrating forward and backwards in the x direction. But guys, look at this pulse of energy. Notice how the pulse of energy travels also in the x direction. So for example, as you see this pulse right here, this pulse of energy starts right here and it travels all the way throughout the length of the slinky. So in other words, the pulses of energy are traveling in the same direction that he's vibrating his hand. So well, the point is that the pulses of energy, they're traveling in a direction that is parallel to the direction of the vibration itself. Okay, so that's the difference between a longitudinal wave and a transverse wave. Okay, so I'm gonna keep this playing in slow motion. That's the longitudinal wave. Y'all can clearly see how the pulses of energy are traveling. And notice how that's different. That's different from the transverse wave. So the transverse wave, again, the wave is still traveling in this way along the x direction. At least the pulses of energy are traveling in that direction. But notice his vibration of his hand is side to side, side to side. Okay. So that's the difference between a transverse wave and a longitudinal wave. Okay. So everybody got that? That's important to know because that's going to be on the assignment. Okay. So once again, in a transverse wave, the vibrations move perpendicular to the direction of the wave itself. Okay. And we kind of see that here. Whereas in a longitudinal wave, the vibrations move parallel to the direction of the wave motion itself. Guys, sometimes in nature, you can actually, believe it or not, you can actually get waves that have both longitudinal properties and transverse properties. So let me give an example of this. So like imagine an earthquake. An earthquake is an example of both a transverse wave and a longitudinal wave. Like it's both waves combined. It's in fact the transverse part of the earthquake that does the most damage. But an earthquake is a good mixture of both transverse waves and longitudinal waves. Okay. So there's something to keep in mind. Before I move on to the next page where we work out actual examples, I want to be sure everybody in here understands the various components of waves, the various parts of waves. So whenever we're talking about waves, Okay. Um, so there's a few terms I need for you guys to know. Um, I need for you guys to know what is the crest and what is the trough of a wave. Okay. So guys, anytime you look at a wave, the crest by definition is always the highest point on that wave. It's the maximum. So this point right here is referred to as a crest. This point right here is also referred to a crest. Okay. So the crest is always the maximum point on the wave itself. Okay. The trough, on the other hand, the trough is the minimum point on the wave. Okay. So this is a trough, and that is a trough. So everybody got that? The lowest point on your wave is referred to as a trough. The highest point is referred to as a crest. Okay. So the maximum point and the minimum point. Okay, the maximum point is a crest, the minimum point is a trough. Okay, so those are two terms I need for you guys to know. Okay, when it comes to describing waves. Okay. Also, you guys need to know what is wavelength. Um, so, guys, if you have a wave, basically what the wavelength is the length of that wave for one cycle. I'm gonna say it again. It's the wavelength just means how long is that wave for one cycle. It's the length of the wave. You guys, there's more than one way you can measure the wavelength. You can either measure the wavelength from crest to crest, or you can measure the wavelength from trough to trough. So, for example, look at this right here. Look at this distance. Look at this distance right here from this crest to that crest. Okay. So the length from crest to crest, if you notice this position here is at 0.75 meters, whereas the position of this crest is at 1.75 meters. So if you do 1.75 minus 0.75, you get 1 meter for this entire length. Okay. All right. You coming back? Are you coming back? Okay. All right. Well, you have a good one. All right. If I don't see you, enjoy your spring break. All right. Bye, Lauren. I won't. I won't. Bye, Lauren. Okay, guys. Um, so the length here of this wave from crest to crest is 1 meter. So we call that the wavelength. And guys, notice you're going to get you're going to get the same distance if you were measure this from trough to trough. Okay, so that is what the wavelength is. Is how long is the wave for one cycle, basically. How long is the wave for one cycle? Also, guys, I need you guys to know what is the amplitude. What is the amplitude of a wave? And this was something that we talked about last time. Remember what the amplitude of the wave is. The amplitude just means what is the height of the wave as measured from the midpoint. So, like, if this is the midpoint right here of our wave, that's the midpoint, and this is the very top point of the wave, okay, the amplitude is just basically the distance from this point to this point. So it's the height of the wave. Okay. So this distance from here to here, that is referred to as the amplitude. So in this case right here, the amplitude of this wave is 4 meters. Again, it's the height of the wave as measured from the midpoint. And of course, guys, you can also measure the amplitude like this. You can also measure the height of the wave going from the midpoint to the minimum. So in other words, you can measure this point this height right here, which is also 4 meters. Okay. So that's how you figure out what is the amplitude. It's just the height of the wave as measured from the midpoint. Okay. All right. So last thing that I want to do to close out the class, I just want to go over a few of these problems here on the back so that you guys have an excellent understanding of how to do the assignment. Okay. By the way, if you guys need the attendance form, let me go ahead and drop that in the chat box for you guys. Guys, please click on that and get that filled out if you have not done so. Okay, so Guys, let's start by looking at this section here where we're trying to figure out which of these represent wave motion and which of these do not. Okay. So look at this. Look right here where it says FM radio. Okay, so FM radio, basically, guys, when you're listening to the radio, think about what you're listening to. You're listening to sound. Remember, sound is a wave. You guys should know that, right? You guys have heard of sound waves before. Sound is a wave. So if you listen to the FM radio, then yes, the radio is clearly emitting waves. So yes, this will be an example of wave motion. Okay, because sound is a wave. What about a car going at 70 meters per second? So I think what they're imagining here is just imagine it's a car just moving straight along, going like this at 70 meters per second. In this case right here, guys, this is an example of linear motion. This is not an example of harmonic motion or wave motion. So since this is not an example of wave motion, we're going to put no. What about a clock pendulum that's swinging back and forth, back and forth? Is this an example of wave motion? Yes. Ocean waves? Yes. Obviously, water, that is a wave. Music, again, you're listening to sound. So, yes, because sound is made up of waves, specifically longitudinal waves. I'm a bulldozer. And guys, I think what they're imagining here just a bulldozer just traveling, in this direction. So in this case, that would be a linear motion. So that would be no. Earthquakes. This is definitely an example of waves, right? Because when earthquakes happen, the earth vibrates. And cell phones. When you're on your cell phone, you're listening to sound, and so sound is an example of a wave. Okay, so yes. Right, so when you're listening to a cell phone, you're specifically listening to sound waves. Okay. All right. Any questions there on that section? Okay, let's look at this right here. So I want to look at these two questions right here. It says a wave has a period of 4 seconds. Find its frequency. Well, guys, y'all know how to find frequency. Frequency is just 1 divided by the period. So 1 divided by 4, in this case, is equal to 0.25 hertz. Okay. So I just wanted to go over this because even though we talked about this last time, I wanted to go over it again because there are some questions on the assignment where you have to find period and you have to find frequency. Okay. What about this right here where it says a wave has a frequency of 2 hertz? Find its period. Okay. So if you know the frequency, you can easily find the period by just doing 1 divided by the frequency. In other words, 1 divided by 2 is equal to 0.5 seconds. Okay, so that's super easy. You guys will have to do it a few times on the assignment, so just want to be sure to go over that. Okay, I want to basically close out this lesson by looking at these two graphs here, and I just want to analyze a few things on this graph here. So right here where it says starting at 1 meter, where does the next cycle end? So guys, if you look at your x-axis, we have position here in meters. So if I was to start here at 1 meter, where would the next cycle end? So guys, when I go like this, go up and then come back to that point, okay, the next cycle ends there. So starting at 1 meter, where does the next cycle end? It ends at 3 meters. Okay. How many wavelengths long is this graph? Well, guys, if you want to know how many wavelengths long is this graph, you just look at the number of cycles that are represented. And we talked about this last time. So if you look at this graph here, notice right here, this is 1 cycle. Okay, so that's 1 cycle. And then here another cycle starts and another cycle ends. Okay, so here I have two complete cycles. So since I have two complete cycles, that means I have two complete wavelengths represented there. So this graph is two wavelengths long. Okay, so that's a cycle and that's a cycle. Notice how the curved line in red is exactly um, identical to the blue line. Okay, so that's a cycle. That's a cycle. We have two complete cycles there. Okay. What about the wavelength? Guys, remember what wavelength means? Wavelength means the length of one cycle. The length of one cycle. So, and there's multiple ways we can measure wavelength. We can measure it from crest to crest or trough to trough. If we look at this, if we measure this from crest to crest, you notice this right here, the length of one cycle is 2 meters. So I'm going to put 2 meters for the length of one of those cycles. Okay. Lastly, let us look at how do we figure out what is the amplitude. Okay. Remember what amplitude is. Amplitude means the height of the wave as measured from the midpoint. So now here it's kind of a little difficult to see what the midpoint is because notice this line isn't centered on 0, this curved line. So we can easily figure out the midpoint by doing this. This right here, that is the minimum point. That right there is the maximum point. So let's count the amount of squares from top to bottom. So there's 1, 2, 3, 4, 5, 6. So if there's 6 meters from top to bottom, clearly the amplitude will have to be 3 meters, okay? Because that's what the amplitude is. It's the height of the wave as measured from the midpoint. Any questions there? Okay. Right here, and again, I'm just going to do a few of these. I'm just doing enough so you guys get the point. Right here where it says, how many number of complete cycles do we have here? It should be obvious to you guys how many number of complete cycles we have here. So like, that's a cycle 1, that's a cycle 2, that's a cycle 3, that's a cycle 4. So we have 4 complete cycles represented here. What is the wavelength? What is the length of one of these cycles? Well, if you look at it, so the length of one of these cycles is just 1 meter. What is the amplitude? The amplitude is the height as measured from the midpoint. So here it would be 2 meters. Okay. Let's look at this last one right here. Look at this question right here. It says, starting at 1.5 seconds, when does the half cycle end? Okay, so now notice on this graph right here, along our x-axis, instead of plotting meters, we're actually plotting time, because at the bottom here it asks for period and frequency, so that's why they gave us a time here. But let's start right here where it says, again, starting at 1.5 meters, when does a half cycle end? So if you start at 1.5 meters, you go from there to there, that's obviously one complete cycle. So that means, where is the half cycle? That means a half cycle will have to be here, right? Because, so from here to here is a half cycle. Well, I'm sorry, from here to here is a whole cycle starting at 1.5 seconds, which means from this right here is half a cycle. So when it says, when does half a cycle end? Starting at 1.5 seconds, it would be at 2.5 seconds. Okay. How many number of complete cycles do we have represented here? Okay. So remember how to find the number of complete cycles. You just look at how many times the wave repeats itself. So this is 1 cycle, 2 cycles, 3 cycles. Okay, notice that wave repeated itself 3 times, right? Because each curved line looks exactly identical to the line before it. So here we have 3 complete cycles. Okay? We have 3 complete cycles. Okay? So guys, what is the period? Remember what period means. Period just means the amount of seconds in one cycle. So if we look at our curved line in red here, that represents 1 cycle. Okay. So what is the period for that curved line in red? If you notice, it's 2 seconds. So the period is 2 seconds. Okay. Now, if the period is 2 seconds, what is our frequency? Remember what frequency is. Frequency just means 1 divided by the period. 1 divided by the period. So I'm going to do 1 divided by 2, which is equal to 0.5 hertz. And lastly, what is the amplitude? Remember, the amplitude just means the height of the wave as measured from the midpoint. Hopefully you guys can clearly see here that this wave is centered at this point right here. It's centered about the 0 axis, right? Because you have half the wave above that point and half the wave below that point. So that means the amplitude of the wave, the height of the wave here is 4 meters. So amplitude here is 4 meters. Okay. Any questions? Any questions for me? Remember, this video will be on YouTube for you guys whenever you're working on the assignment, which is already up in Schoology. Okay. So if you guys have not filled out the attendance form, please do that before you leave this Zoom call on today. Guys, if there are no immediate questions for me at the moment, you guys are free to go. Have a good day, everyone.